speaker. Hello, everyone, and welcome to the SLDS monthly webinar. My name is Jamie Spicer. I am an assistant professor at Wake Forest School of Medicine, and I am organizing this webinar series that is sponsored by the section on statistical learning and data science of the American Statistical Association. Today, we are honored to have Nesime Tatbul talk about data science and time series analysis. Nesime is a senior research scientist at Intel Labs and the Massachusetts Institute of Technology's Computer Science and Artificial Intelligence Lab. She serves as co-PI for MIT's Data Systems and AI Lab, jointly funded by Intel, Google, and Microsoft. Her research interests are broadly in large-scale data management systems and modern data-intensive applications, with a recent focus on advanced time series analytics and learned data systems. The talk today will be about an hour. Please type questions into the chat box and we will hold them until the end of the presentation. We should have about 30 minutes for discussion. The webinar is being recorded and will be available on the section website. I'd like to thank our speaker and the sponsor of this webinar, the Statistical Learning and Data Science section of the American Statistical Association. And Nesime, I'll turn it over to you now.
Thank you very much, Jamie. Thanks for the kind introduction and also inviting me to speak here, both to you and Sarah. I would like to thank for providing this opportunity. This is a new community to me. I will be speaking for the first time, so that's very exciting to me. So as you also mentioned in the introduction, my work recently has focused on a bunch of different problems in the intersection of machine learning and data systems. And today in this talk, I will be mainly talking about some of the recent research I have been doing in building practical data science tools for time series analytics. And what I'm going to be talking about today is based on multiple collaborations across Intel, MIT, Brown, SLAC, and Eco Polytechnic. Time series is one of the most ubiquitous types of data in our increasingly digital lives, and it has many diverse applications from Internet of Things to finance to telemetry, and larger volumes of time series data are being generated by these applications every day, and there is a substantial demand for data systems to store and manage such data. And in fact, popularity of time series databases compared to other data types has been trending recently, as it is also evidenced in this chart, which is a time series itself. Time series capture rich temporal patterns, rich temporal phenomena, and we need advanced analytical and AI capabilities to understand and react to such patterns. And again, this chart from a recent report shows that, in fact, time series comes right after structured data in terms of carrying the highest potential for AI value in applications. So, having said that, let me give you a concrete example application. This comes from the domain of cloud observability. In order to monitor and maintain complex cloud applications against things like bugs, failures, or performance issues, cloud observability systems need to collect, store, and analyze large volumes of time series data every day. And this time series data can come in various different forms. It's heterogeneous. It can be metrics or events happening in the system, logs of systems events, and traces collected from microservice runs, and so on. In this kind of a setting, performance anomalies, like in this example on this picture, such as a slowdown in server requests, should be identified and tracked back to their root causes, so the right corrective actions can be taken. And oftentimes this needs to be done in an interactive manner by humans in the loop. With collaborators from SLAC and Brown University, we recently conducted a case study over SLAC's observability use cases. As many of you might already be familiar, Slack is a cloud-based business communication platform with millions of users around the world. When unexpected systems problems occur, as shown in this example on the slide, this example comes from a real service disruption incident that happened last year. Slack's engineering teams, they all come together exploring patterns and correlations across petabytes of operational time series data that they collect and that is visible to them through Slack's monitoring infrastructure. And the critical measure in these kinds of situations is to minimize the time to insight, meaning the time it takes to understand what's really happening in the system and why. So the engineering team can quickly find a fix and return the operations back to normal. So to reduce time to insight, it's really critical that an efficient and scalable data management infrastructure is in place. In our case study, we try to characterize the requirements of such an infrastructure, and we identified 4 different categories of time series. And we identified what types of query workloads need to run over them. So this way, we can identify what guiding design principles should be followed when building such systems. So we have a paper about this. In this talk, however, I will be speaking less about data management and more about data analytics. And I would like to briefly highlight one of these data types over here, which we will come back to later in the talk. It's metrics. Metrics provide numeric measurements of system performance and availability at a specific point in time. And as can be seen from this case study, metrics in cloud observability can be really high in volume, and they have to be also kept around for a while, not just for a few days, but sometimes for a month or more. So this amounts to large quantities of numeric time series to be stored and analyzed. In this talk, our focus, as I said, will be on analytical techniques on such time series. And when we talk about time series analytics, really time series analytics embodies all big data challenges that relate to scale, complexity, and diversity. And mainly time series can be really high in volume in the rate of data generation or its dimensions. These dimensions can have correlations or dependencies among them, and which may require us to analyze them in a multivariate fashion. The patterns of interest we're looking for on these time series can not be precisely known in advance. They can come in a variety of lengths and shapes. Values can vary by context or may have intricate causal relationships. And on top of this, the data can be noisy and irregular and so on and so forth. So all this variety also shows itself across diverse application domains. And using machine learning and more recently deep learning techniques can greatly help here, but it also comes with its own challenges. For example, finding good training data can always be an issue. So given all of this, how can we navigate through all this complexity and build practical solutions that can be reliably deployed in the real world? That is the question that we are asking in our research. In the rest of this talk, I will focus on anomaly detection and explanation, which is a popular task in time series analysis. And I will give examples from our recent efforts in building tools to make this task easier to accomplish for the data scientists, for the domain experts. And first, I will start with the tools that we developed for evaluation and benchmarking. And then I will also briefly go over a few other tools that we built, mainly MetroViz and Dagger for interactive data exploration. And then I will conclude with a brief discussion of future directions for this kind of research. Anomaly, I'm sure you are familiar, it's quite popular these days, this problem. Anomaly is something that deviates from what is expected, like this in this simple example. And like we also saw in the Slack case study, detecting such anomalous patterns and responding to them can be very mission critical. And the other aspect of this is that by having anomaly detection capability in the system, this capability can help guide us, our attention or resources to the information that matters the most for the application. So especially when we are dealing with high volumes of data, focusing attention on anomalous parts of the data can be important. Equally important to detecting anomalies is discovering their explanations for how and why those anomalies may have happened, because that informs the reaction, the response that we can take in order to respond to such anomalous situations. And what do I mean by explanation is a human readable, some kind of human readable compact representation characterizing or giving useful information about an anomaly. And this representation can be a logical formula, a predicate, sometimes it's a decision tree or an expression about future importance scores and so on. In the simple example, I have a conjunctive predicate here with two features, feature 4 and 5 from the dataset, saying that this anomaly that was detected in the example happened when the total processed records and the total received records were above certain values. For the purposes of this talk, for the rest of the talk, it is sufficient to understand the high-level intuition behind these concepts. So I will not give too much formalism about these, but if you're interested, you can find them in the related papers that we published. So I'd like to start by making two key observations about time series anomalies. These observations especially motivated our work on evaluation. First of all, most complex anomalies occur over a period of time, which we refer to as range-based anomalies. And here is an example from Chandola's survey paper on anomaly detection, showing a range-based anomaly in human ECG readings. As can be seen here, as opposed to point-based anomalies, the anomaly here is meaningful over a collection of values and in a given context. And that collection of values is not a random collection. It's actually a collection of values that are consecutive in the timeline. So that's an important observation to make. And secondly, anomaly detection applications can be very diverse, as we also talked about before. And these applications may have domain-specific preferences. For example, in certain domains, such as cancer detection or real-time detection systems, detecting the beginning of an anomaly or detecting an anomaly as early as possible is important. This way it can enable taking an early response to the anomaly. While in other domains like defense or emergency braking systems in autonomous vehicles, detecting the later stages of an anomaly can also be important in order to avoid taking, premature or irreversible actions. Likewise, the domains may also have different tolerances to different types of classification or detection errors. For example, in cancer detection, false negatives, meaning those for real cancer anomalies that are falsely predicted as benign, are to be avoided in order not to risk the patient's lives. So in other domains, the attention may be more on false positives as errors. So we need a flexible way of accommodating these different varying application needs about the detection criteria and results. So given these, one of the fundamental questions is about evaluating the results of time series anomaly detectors. How do we evaluate them? A common way to evaluate classification techniques is precision recall. And for point-based data, this works really well. Using these simple formulas, as also illustrated here, one can quantify very easily how many of the real anomalies are correctly identified with respect to the total number of predicted or real anomalies. Unfortunately, for range-based data, like in time series, these point-based models, they cannot sufficiently capture the more complex detection situations that can happen. As shown in the simple example, the anomalies are not points, they are ranges. And real anomalies and predicted anomalies, they don't usually match perfectly. In fact, range-based anomalies are typically detected partially, and sometimes in multiple fragments. And furthermore, as we talked about on the previous slide, there may be domain-specific criteria, such as time bias. Time bias meaning here the urgency of when an anomaly is detected and reacted to. Is it detected in the earlier part of the range or later parts of the range? So the bottom line, based on these observations and examples, is that we need a model where we can express partial detection situations on range-based anomalies, as well as supporting flexible time bias expectations of applications. So we looked at in addition to precision recall, classical precision recall, where these precision recall criteria based on false positive, false negatives can be expressed, and their combinations using F-score in order to weigh the relative importance of recall to precision. We looked at what other evaluation techniques are available for using in this domain, and a more recent scoring model called Numenta was relevant here. What we found there, again, the anomalies are based on point-based data, so that doesn't really help with ranges. And the other thing we found was that while Numenta was specifically designed for streaming data, so they can capture the early detection use cases and real-time use cases, that it's only specific to that one situation. And there are some issues also using this model in practice, which is actually documented in a recent publication by others. So the other work that we found in the literature was from the activity recognition domain. Here, researchers also look at event patterns on data from activity sensors. So they look at ranges of these patterns and how they get fragmented and so on. But again, we didn't fully find what we were looking, especially we didn't find support for flexible time bias there. So in order to fill this gap that we identified, we proposed a new mathematical framework where we extend the classical precision recall model to range-based data. So we start with the classical one, and we try to figure out what's missing in that model that is preventing us from express the requirements of time series anomalies. When we were doing that, we followed 3 design goals. Expressiveness in order to capture the unique criteria for range-based anomalies, such as positional time bias. And second, flexibility in order to provide adjustable parameters to properly weight the criteria differently for supporting different applications. And extensibility, so we provide a modular structure in our framework to enable new domain-specific extensions in the future if necessary. And based on these design goals, our model provides 4 customizable parameters. These are carefully injected into the classical precision and recall formulas. What are those parameters? We have alpha parameter. This is used to reward detecting the existence of an anomaly range. So if an algorithm is successful in detecting the existence of the range, but not the range in its fullness, then alpha parameter provides an opportunity to partially reward that situation. And oftentimes this is of course not enough. So we have the omega parameter in order to reward the detection of the as much of the anomaly range as possible. So we have much better coverage. And there is a delta parameter in order to reward detecting the more important portions of an anomaly because of this positional time bias concept that I talked about. And there is a fourth parameter called gamma, and we use that to reward detecting the anomalies in a non-fragmented manner. If there's a single anomaly, that's a single range, we don't want the algorithm to detect this as if it consists of multiple fragments of anomalies, which might be confusing to the users because they would not have a good way of figuring it out whether that corresponds to a single anomalous event versus multiple real anomalous events. So I'm not going to go into the details of the formulas, but I will show you some examples. Here, I'm showing examples for how our model could be customized and used in different applications. From my earlier example, actually, cancer detection, defense, and emergency braking. The pseudocode fragments that I show above, they show how to set the omega and delta functions in order to match the needs of these three example domains. Again, omega was for capturing the how big is the range that the detector was able to cover, and delta was for which portion of the range was being detected. Is it the front end of the anomaly? Is it the end or somewhere in the middle? So, for example, by setting the delta positional bias parameter to front end, this model can be customized for supporting early detection use cases like cancer. And for defense, delta can be set to back end and middle for emergency braking. Of course, I simplified the example a little bit. There are other parameters. All four parameters, they need to be set here. And I would like to also make a note of that our model subsumes the classical point-based model, and it provides a generalization of that model. So when we set the parameters, those four parameters in a certain way, that takes us back to the classical point-based model. So it's really builds on it, generalizes what's already out there. So to demonstrate the usefulness of this approach, we performed an experimental study. And in this experimental study, we took 7 different anomalous data sets from the literature. Actually, some of them are real data sets with anomaly labels, and some of them are artificially generated using our generator. And we took also 3 different anomaly detectors. And we have shown or we have compared how we can score the results of these detectors across those 7 different data sets. And we score them using the classical point-based model, the Numenta model, and our new model. And we try to show usefulness in a bunch of different ways. First of all, we try to show that our model can behave like the other models if we intentionally tune it in that way. And then we also try to show it can actually express other criteria that those models cannot. In the classical case, it was easy to show that our model subsumes to the classical one by setting the parameters to those default values. So in those cases, across all the detectors and the data sets, we achieve exactly the same precision recall or F-score values. But if we also start changing the additional parameters we introduce, like the delta parameter for positional bias, as in this example, then our scoring formulas start showing results that the other the classical model cannot capture. So we have the sensitivity to those different parameters that is not possible to express and measure with the classical model. We tried to do a similar experimental study with Numenta. And of course, since Numenta follows a completely different mathematical structure, we cannot do an apples-to-apples comparison numerically against that. But our goal here was to show that we can actually mimic or simulate the trends of the Numenta model if we set the parameters such that our model behaves as close as possible to the Numenta model. And in the result here, we should not really look at the absolute values, but the trends. And our model was able to capture the trend that the Numenta model is following, the accuracy scores going down from left to right. And I circled one particular case there where actually our model behaved differently from what Numenta was saying. And then we analyzed the data set, the space shuttle data set, to see what's happening there. And we saw that a small number of mid-range real anomalies and a large number of mid-range predicted anomalies were observed in that data set. And so it had more false positives and true positives than the other data sets. And this reflected in the smaller precision score and larger recall score there. And Numenta model is designed to favor precision over recall. And because of this, because Numenta heavily penalizes false positives in a disproportionate way compared to recall, it showed in our results. So I think what this means is that our model captured something, again, that couldn't be done otherwise. And in the third result, what we tried to do was, what if we didn't have a single detector, but multiple detectors, like LSTM-based ones, and this greenhouse and luminol from the literature. So if we let them run on one of the real data sets we have, New York City taxi data set in this case, and then scored the results, what would we find? We found that actually, interestingly, the different scoring techniques ranked them differently. So again, the absolute values here are not important. Relatively, we are looking for which detector was found to be performing better than the other ones. So our model disagrees completely with what the other scoring models were saying. And again, we went into the details of the data set and the results, and we have seen that actually we were able to capture some subtle things in the results that, again, classical and Numenta ignored. In fact, for example, for the luminol detector, where Numenta strongly favors, we found that this detector misses completely one of the three real anomalies in the dataset entirely. So I think with these results, we were able to show that the SNP framework can actually help evaluating and maybe even building when training these detectors in the future. And so there is a paper about this work we published at NeurIPS a few years ago, and there is also a tool that we implemented, which is open source. And the tool was C++, but I think some other people from the machine learning community, they implemented Python versions of this as well. And those are published at the Papers with Code dataset as well. So let me now start talking about some follow-up work that we did after this evaluation framework. What we did is we integrated the evaluator from this work to a new benchmark and an experimental platform that we built for anomaly detection over high-dimensional time series. And the platform, this benchmark is called Exatlon, and Exatlon has been largely motivated by the fact that in the literature we lack open data repositories and benchmarks which could serve as like a common experimentation ground for enabling reproducible research and experimentation in this domain. And here we are not only covering anomaly detection, actually explanation discovery is also another task that comes with it. And so I think it's the first benchmark that's trying to address both of these in an end-to-end fashion. And what does this benchmark consist of? It mainly consists of three components. First, we provide a real-world time series dataset that we constructed. The dataset has both normal and anomalous traces in it. Then we provide an evaluation methodology for both anomaly detection and explanation discovery. And we also provide a data science pipeline which can be used to develop and evaluate such techniques. So let me give you some details about each of these components. But the benchmark itself, the data set, and all the code is also open sourced on GitHub. The benchmark models a use case scenario based on Spark application monitoring. This is somewhat similar to the metric monitoring problem that I talked about for Slack in the Slack case study in the beginning. So the Spark workload here consists of 10 stream processing applications. These applications are analyzing user click streams collected from a real website. And the data comes in the form of user ID, timestamp, and URL tuples coming in batches, in streaming batches. There is also static PageRank information stored in the system in HDFS. And that's showing the PageRank of each website URL. And so in the each of the applications, we either process the streaming data through a query, or we sometimes join it with the stored data, the PageRank data. In fact, the query example, SQL query example I'm showing on the slide is for such a join between the PageRanks and user clicks. So to generate the data, what we do is we pick 5 applications out of 10 applications randomly every time. We run them concurrently on a 4-node Spark cluster for a period of time. And during that run, we collect metrics. And we do this repeatedly. During each of the runs, we collect more than 2,000 Spark and operating system metrics. And during some of the runs, we ran a special program called the Disruptive Event Generator. This introduces real anomalies to the execution. And the traces that we collect during those time periods, they contain various types of anomalies. And in total, we generated about 25 gigabytes of data, and 15 gigabytes of that contain the anomalous traces. To give you some more details about this data set, there are 93 traces in total, and 59 of those traces are undisturbed, and they represent basically the normal behavior of the applications. The remaining 34 traces contain multiple instances of these 6 different types of anomalies. The first 3 of the anomalies are input related. Things like input rates getting bursty for a duration, or input rate getting bursty and then causing a crash at the end, or input is stalling by going down to 0 for a while and then coming back up again. Other than the input-related ones, we also have things like type 4 anomaly for CPU contention, where our disruptive event generator is running a Python program to consume all the CPU cores on a particular node, and during that time, CPU gets contended, and that impacts the performance of the regular applications running on Spark. And then there are 2 other ones for failures on Spark's drivers and executors. And all in all, the data set contains close to 100, like 97 anomaly instances. and these are all labeled together with their root cause intervals. So root cause is for the intervals when the disruptive event generators were running. So we precisely know when we started those and we ended those. And then the extended effect intervals showing the impacts of that disruption on the metrics. And these were labeled using domain expertise, hand labeled. So next, let me show you a few actual anomaly instances from the data set. These are for the input related ones, T1, T2, T3. And here we are basically showing anomaly intervals between the red vertical lines over the time series of these three selected metrics. And number of processed records are shown in green, scheduling delay in orange, and then processing time in purple. For type 1 anomaly, we see 3 anomalies when the input was bursty, causing all these 3 metrics to increase during the anomalous period. And similarly, for type 2, we see a single anomaly in this case because it's bursty input until crash. At the end of the anomaly, the system crashes, so we really experience one long anomaly. And again, the metrics are all going up during this period, and similarly, for type 3, we see the impact of stalled input manifesting itself as number of processed records going down to 0, and the input is stalled, and everything comes back up again once the stalled input gets back to normal. So I'm showing these examples to show you, how the anomalies look like, and they actually carry some useful and interesting signals in them, and we'll see how successful the algorithms will be able to pick up these different kinds of anomalies. And then given this data set, the second component in the benchmark is the evaluation methodology. So we designed a benchmark to evaluate both anomaly detection and explanation discovery algorithms, and we do that along 2 orthogonal dimensions in terms of their functionality and in terms of their computational performance. And for each of these, we provide a well-defined set of evaluation criteria and metrics. For both anomaly detection and explanation discovery, the evaluation criteria is multi-leveled. So we can capture increasingly more challenging requirements for the algorithms. For computational performance, we provided 3 complementary criteria, and these are for training scalability, inference efficiency, and explanation discovery efficiency. And these can be also evaluated by varying the dimensionality and size of the dataset. Our benchmark primarily targets certain types of methods that we focused on, but I think the benchmark actually can have broader applicability, and we discussed that in the paper that we published. Let me go through the scope that we had initially. For anomaly detection, we target mainly range-based anomalies over high-dimensional time series, like in our dataset, and using semi-supervised deep learning-based anomaly detection techniques, as these are currently very popular, and they are good at catching or detecting anomalies in a better way than some other techniques. And we also provide different learning settings for anomaly detection. And these learning settings are mainly about how the training datasets are prepared and used by these algorithms. So again, we can experiment with the impact of different data sets on the detection performance of different algorithms. For explanation discovery functionality, we target both model-free and model-dependent methods in the literature. And for performance, as I said, we have 3 metrics, but we can vary the dimensionality and the size of the data set in order to see how the performance changes with those. For evaluating the anomaly detection levels, as I said earlier, we use the evaluation framework that I introduced in the beginning of the talk. And the essential metrics that we used were precision and recall. And precision intuitively for evaluating the prediction quality, and recall for evaluating the prediction coverage. Let me show this more concretely on a simple example. In the example, we have 4 real anomalies shown in blue and 4 predictions shown in yellow. And then the green sub-ranges show the partial anomalies that were successfully detected with this detector that we are assuming. And so for let me go through the 4 different levels of anomaly detection. We have AD1 through 4 and illustrate what they're actually trying to measure here. For AD1 anomaly existence, we are interested in the existence of the anomaly. So tell me if there is an anomaly. And it is sufficient to report, in this case, an anomaly during the anomaly interval. And in the example we have, except R2, all anomalies are found. For AD2 range detection, we are trying to detect as much of the anomaly as possible. In this example, about 50% range coverage is achieved for all the found anomalies. For the 3rd level, early detection, we are trying to report as soon as possible the beginning of an anomaly. And here it is achieved by R3 and achieved for R3 and R4. And the last one is for detecting anomalies for exactly once. Each anomaly should be reported exactly once, and R4 was detected in a fragmented manner, so the algorithm that behaves this way should be penalized for that. So now, given these requirements, how do we actually quantify the accuracy? It's pretty straightforward, actually. We use our range-based model from the first part of the talk, just set its parameters according to the expectations of these 4 different levels, and that gives us the metric values for precision and recall for these detectors. And for explanation discovery, we have defined similar metrics and criteria. Mainly, we represent an explanation as a function of features. In this case, in the example, a predicate over the feature parameters. And we have 2 levels, local and global. And basically, the local one is measured per anomaly instance, and the global one across all instances of a certain anomaly type, like the type 1 anomaly. And when it comes to the metrics, there are 4 of them, and these apply both to the local and global levels. Conciseness is about how compact or small the explanation is, and it's measured based on the number of features that's used in the explanation. People are better at understanding more compact and concise explanations. So the goal here is to find explanations that are as short as possible. Consistency is about how similar the explanations are for similar anomalies. If an anomaly is of the same type or happens in a similar context, we expect to see that in the detection. There is a variant of consistency which is called normalized consistency, and here we measure it with respect to the size of the anomaly, because consistency oftentimes is easier to achieve if the anomaly is also more compact. And then we have also an accuracy metric in order to measure the precision recall of the explanation if the explanation was applied as a predictive model over the data. And so we basically define these metrics for both the local and the global levels. And the global levels can be seen as the aggregated variance of the local one. These are all formally defined in the paper. Next, I would like to move on to the 3rd component of the benchmark. That's the platform itself. So here we provide an end-to-end data science pipeline for anomaly detection and explanation. This pipeline takes the raw data sets from our benchmark and it turns it into anomaly detection and explanation discovery results together with their evaluations. It's modular and extensible, so other techniques can also be added on top of this platform. And we created multiple variants of the pipeline steps in order to mix and match them, and so we can run different experiments and compare them. The first pipeline step is for data preparation. It's shown in blue here, and it consists of mainly data partitioning and data transformation steps, which prepares our training and test data sets. Here we also have things like dimensionality reduction, sampling, and so on. These are all configurable, as I said. And then comes the second step shown in green. That's for anomaly detection steps, basically. And it involves building a model for the normal data and then using it to derive outlier scores for the test records. And then finally selecting a threshold on these scores to assign final predictions. And the outputs of these steps are fed into the evaluator in order to score them, and at the same time fed into the explanation discovery modules to look for their explanations and also evaluate the explanations themselves. So we actually also built a demo based on this platform and published at VLDB, showing how this platform can be used for experimentation and analytics purposes in realistic applications. So let me also quickly show you some results. We have a lot of results. They are in the paper that we published about the benchmark, but I will pick one of those results to present here. In the experimental study, we tested different options along the different modules of the pipeline. We have learning settings, as I said, to prepare our training data sets differently, whether we take the traces for a single application versus all of the applications, or whether we only stick to the examples in those data sets themselves, or we peek into the testing data sets and get some normal traces from there and inject them into the training data set to enrich the contextual data. So all of these can be combined, and different types of training data sets can be created to experiment with. The dimensional reduction comes in two options in our current implementation. We have a PCA implementation. We also have a custom one where the features were manually selected. For normality modeling, we provide implementations for both forecasting and reconstruction-based deep learning techniques from the literature, mainly LSTM-based model and autoencoder and bidirectional GAN. For threshold selection, again, we took three techniques from the literature. We haven't implemented our own. We took from the literature and applied them. We also created different granularities of our data at the trace level, at the application level, or global across all the data sets, all the traces we have. We tested for 4 different AD levels. We also did similarly for the explanation discovery. We had 3 different techniques. 2 of these were model-free techniques from the literature. 1 was model-dependent one. And again, we tested them across both the local and global explanation discovery criteria. So in the selected experiment, for each of the 3 anomaly detection methods, we are showing the anomaly detection results across different thresholding techniques. We show them per anomaly detection level from AD1 to AD4, per deep learning method from LSTM to BiGAN, and we are showing the precision recall and F-score measurements that correspond to those. And a couple of observations here. First of all, the task gets more challenging for all 3 methods as we increase the AD level expectations from existence to exactly once. We observed that the BiGAN technique does the worst overall, and our explanation for those results were because of the fact that the GAN takes too long to converge in the time given to the experiments. And across all the results, the autoencoder turned out to perform the best. And the reason for that was because the outlier scores for autoencoder were coming out to be much smoother than the others, giving it better separation ability. So we have detailed analysis of those results in the paper, but I included one snapshot of the results here for T4, where we are contrasting the outlier scores of LSTM against autoencoder, and then we can see the difference there, how smooth the results were for autoencoder versus the more spiky results of the LSTM one. And that reflected in all of the results. Except AD1, interestingly, LSTM was able to do better on and AD1, and there being spiky didn't really matter. It actually helped LSTM because it was about catching the existence of an anomaly for AD1, and it was fine to be not smooth in that case. So that was interesting to see. So overall, our experimental study showed that the data set contains a variety of meaningful signals, and these can be picked up by the methods that we tested, and the way we organized our benchmark metrics, criteria, and so on. They helped us to systematically challenge these methods and compare them. Of course, more studies are needed to explore this benchmark in its entirety. These were just initial results showing the key characteristics of the benchmark. So now I will switch gears and tell you very quickly in the remaining time about two interactive tools that we built for data exploration. The first of these, called MetroViz, is a visual tool for exploring time series detectors and their results. And the motivation behind that work was that developing, testing, and tuning anomaly detectors is not an easy task for a data scientist. First of all, this cannot be fully automated, so a data scientist should be in the loop. And secondly, this happens over multiple iterations. It's rare that a pipeline is built and it just works like that. It needs to be tested and tuned and so on. And so it's really important in that kind of a setting to provide tools with an intuitive, easy-to-use interface, and which is also designed in a way that can scale with large data sets and a variety of different situations that the data scientist can face. So here we try to design a tool which equally values user interface and the backend data system design, so that it can be both usable and scalable. And while doing that, we focused on the unique characteristics of the exploration pattern for this kind of a workload. Time series are oftentimes, they are aggregated at different time granularities, like also in our benchmark, they can come at trace level or application level or different time granularities. And as the user runs the detectors through these different variants of the data set, results are being explored, and sometimes there's something interesting, the user may want to go into details of what's happening and maybe compare multiple scenarios. Some of those scenarios can be hypothetical, what-if type of scenarios. So we try to consider those different situations. The system is still under construction, the backend, but we have a working version today, and we published a demo about it, paying more attention to the front end and some of the data optimizations to support that front end. So it looks like this. The user can select from a bunch of different data sets, can decide on the time granularity of the data set, and how data should be aggregated for those selected groups, whether they should be averaged, summed, and so on. And different detectors can be also connected to the tool, and they can be selected. Their results can be run over the data set. These are pre-trained detectors. And then the results can be compared across these different detectors. There are different settings in order to create what-if scenarios. For example, the user can choose a certain anomalous range and then can manually modify that range. What if the data look like this? Then if I rerun my detector, then what would the detector do? Would it be still an anomaly or not? So these can be tested that way, and then zooming in and out into the data sets to look into the details, various statistics about the found anomalies, how many of them were found by one detector versus the other detector, and maybe some statistics about the length of the anomalies and so on. The second tool I want to talk about is called Dagger. Dagger is for data debugging in Python-based data science pipelines in general. So it's not time series specific, but also works well for time series data sets. So what it does is that given a data science pipeline written in Python, first the user tags certain code blocks in that code, and defines the pipeline blocks. And then when the pipeline runs with a given input data set, then the system logs data for those marked blocks of code and organizes them and indexes them in a database. And then Dagger exposes a simple to use, easy to use SQL-like query language called DQL, Dagger Query Language, in order to interact with that logged data in the database. So the user can analyze what happened as the pipeline was running on that input data, can analyze the intermediate data sets for those blocks, can define data assertions as breakpoints, like in code debuggers like GDB. In fact, Dagger is like GDB for data. So you can define these breakpoints and data assertions conditions about the data should satisfy, and whenever there is a violation, for example, the system will flag that automatically for you. Or you can define splits in order to partition your data set in different ways and run the pipeline separately for those partitions and then compare the results and so on. And the other nice thing about Dagger is that it is integrated to Jupyter's Notebook interface, so it can work together with pipelines that are defined in that environment, which makes it practical to use. So in one use case study, this use case comes from Intel's one of the Intel groups working on business and marketing use cases. We applied Dagger to a pipeline where the pipeline takes data sets about marketing campaigns, what investments were made on what marketing campaigns in the past. And based on that data, the pipeline is trying to forecast where the future investments should be, which type of campaigns were more promising in terms of the benefits that it brings to the business. So the pipeline consists of multiple steps, some data preparation steps to remove errors, and then there's a label generation step, and finally there's the modeling and testing step. And we identified 7 different data debugging scenarios that can happen in this kind of a pipeline. I'm going to show you 2 of those more concretely. The first scenario is about finding data errors. In particular, in this scenario, there is supposed to be a one-to-one match, one-to-one functional dependency between campaign IDs and their categories. And sometimes the data set may have errors and this mapping not necessarily holds. So by using Dagger, we can actually create blocks to log, and then we can create breakpoints where we define this mapping condition. And then once the pipeline is run, then Dagger can automatically tell us where in the data this mapping was violated. A second example I chose is about the model accuracy exploration. What if we defined a pipeline, we ran it, and then we got some results? And the data scientists found that the results, the accuracy is not satisfactory. Then the next step might be generating training data for different time granularities as opposed to looking at the whole data set. But if we looked at the data in quarterly, yearly, monthly, different granularities, and retrain our model, would the model behave in the same way, or would we see different accuracy results? So this can also be done very easily with Dagger. We again instrument the code for the data blocks of the different parts of the pipeline, and then we use the split primitive in order to partition the data set into different time granularities. And then we run the pipeline for those 4 different variants, and we can plot the results. All of this is happening with 8 to 10 lines of Dagger code, basically. So this really makes it easier to specify these different situations using the DQL language and running it behind the Jupyter Notebook interface for the user. So it's supposed to help with the data scientist productivity greatly. And we are currently conducting a study to quantify all these impacts. So I think I'm over time, and I will try to wrap up. So this slide, just to summarize the tools that I talked about. I told you about real applications and challenges around time series analytics and focusing on anomaly detection and explanation as a common task. And then I told you about 2 types of tools, Exatlon and the TSAT evaluator that we built for evaluation and benchmarking. And I told you about MetroViz and Dagger for interactive exploration. We are making these tools publicly available as we build them. So for 2 of those, I provided the links for you, so you can download and try them and give us feedback. We would be very happy. For MetroViz and Dagger, we have them implemented and demos are published, but the code we haven't published yet, and they will be coming soon as well. So with that, let me conclude my talk with a forward-looking statement on the role of time series that I see in future AI systems. So we are witnessing that AI is changing the way we build our applications, not only applications, but also the systems and also how we operate those systems. As we have seen, not only time series is actually very widespread across different application domains, but also I believe it forms a very essential pillar of any AI-driven system. And the reason I'm saying that is that we are seeing some emerging examples in the learned data systems or learned systems in general in that space, where these techniques to learn and self-adapt to different workloads or situations are becoming more and more common. For example, in machine programming systems, where we try to automate software development and maintenance, we are trying to learn from large code bases or the behavior of those code bases in order to automate the tasks in that domain. In instance optimized data systems, we are trying to create learning systems out of learned components so they can adjust to workload and resource variations. And similarly, in cloud services, the cloud services today are evolving at a great pace. And at the same time, it's becoming very difficult to build and operate infrastructure for supporting the new applications there. So in all of these systems, using AI to manage their operations, I think any self-adaptive functionality will require collecting and learning from large time series data. And tying back to the beginning of my talk, we are already starting to see this emerging in the cloud observability systems today. If you're interested in this direction of research, which ties more into some of our projects in the learned system space, I've listed a couple of publications to show you examples of these different kinds of systems. And especially, there are two new papers we have coming up at CSAIL. One of them about instance optimized systems in general for the cloud, and the other one is a metrics storage engine that we have built to support observability in such environments, kind of like in the Slack example. So that brings me to the end of my talk, and sorry for running a little bit over. And
thank you. That was a wonderful talk. I found it so interesting. So thank you for sharing your work with us.
Thank you.
I'd like to encourage the attendees to please put your questions either in the Q&A or in the chat. One of them did come in during your talk, so I'll go ahead and read that one. And everyone else, please add your questions as we're going through this. So SW Hermanson was curious if you've applied anomaly detection methods and filters of data streams.
If I understand the question right, the answer is no. We take the raw data sets from our traces and we try to detect the anomalies themselves. But we do some data preparation ahead of time before we build the normality model and we do the anomaly detection itself. So during those data preparation steps, some selection steps are going on, but these don't use anomaly detections for filtering. These are, mostly techniques that maybe except for the dimensionality reduction PCA, these are not really using machine learning. These are either created manually to experiment with different variations or simple filters like in this experiment, I want to just focus on this trace kind of filters. So there is no sophisticated anomaly detection filtering going on during the data preparation steps, but anomaly detection itself shows up only where we are actually doing anomaly detection. I hope I understood the question right, but that's...
Yeah, so if that was your question, go ahead and write in, if that answered it, or if you would like to unmute and speak, I can allow you to do that also. So I was also interested, this is really outside of my area, but I found it really fascinating. And I really agree with your point that this type of data is present in all sorts of different areas. So I'm wondering if you could give some ideas for resources for people who are interested in learning more about data science for time series analysis and anomaly detection, and what are some good places to start out?
On my slides, I pointed to work that is directly or closely related to what I was talking about. But also, I think if you look at the papers we published and their references, that those could be a good starting point. In those papers, we cover the state of the art, point to selected related work that we took as our foundation. So I think that can be a good starting point as well. And I could also maybe advise to look at data science venues like KDD, where there are tutorials and surveys and various talks on these topics. Especially the tutorials could be a good starting point. I think there was one actually at this year's KDD conference on outlier detection and anomaly detection. I believe both the slides and the video for that one is available as well. So that could be a good starting point.
Great. So I don't see any other questions in the chat yet, but go ahead and type them in if you have anything. I have one other one that came to mind. I'm wondering if you've thought about missing data in the time series that you have. And an example from our department, we have some grants that are looking at wearable technology data. So like Fitbit sensors and there's all sorts of challenges with the time series component, but also because there's missing data kind of randomly throughout the time series. So I'm wondering if you've thought about that and how you might incorporate instances of missingness into kind of the methods that you've been working on.
Yeah, this is a very common problem, and it didn't show up so much in our data set. It was created in a very controlled environment. We had some noise, but that noise came from the natural setting of the Spark system. Like when Spark is running some routine jobs like checkpointing or whatever, which is beyond our control when we created the experimental setup for data collection. So we could see the impact of those in our measurements, but missing value we haven't seen so much. But it's a very common problem, and the closest work I did in that domain is with Dagger, the data debugger. Using Dagger, missing values can be identified, and techniques from the literature like missing value imputation techniques can be applied. I'm not specifically focusing on data cleaning problems, so I cannot give you, detailed algorithms or pointers, but I can assure you that it's a common problem, and there is tons of work that my colleagues are doing in the data cleaning space for exactly that problem. For time series, I think maybe what's interesting to mention is that since this is time-oriented data and there are some trends the data is expected to follow, especially under normal situations. When anomalies happens, this can become much more difficult because you don't know, what anomaly, how it manifested itself in the data sets precisely. So it may be difficult to impute data sets missing values for those points. But under normal circumstances, data trends can be utilized to impute the values or predict what might be missing. So maybe compared to some other data types, it's more interesting to look at data cleaning in the context of time series.
Yeah, I feel like this could have been an entire talk about data cleaning with time series also. It's just such a big challenge in any project with data science.
Yeah, and I think the multidimensionality of time series also could be interesting for data cleaning in the sense that these dimensions are oftentimes correlated. So if you have data for one of the dimensions, you may be able to utilize that when predicting what might be missing in the other dimensions, perhaps. So these are just some ideas that come to mind as I speak to you, but I think it can be a really interesting research direction, especially if you have real data sets, real use cases, as most of the work in this data science domain, I think, is highly driven by use cases. And given that you have a data set you're talking about, maybe you should explore that research direction.
Yeah, there's a whole group of us actually in my department who are working on that type of data, and it's very challenging and fun.
Yeah, challenge is fun.
All right. Well, so I don't see any other questions, but Hermanson said back, very deep and insightful presentation. Thank you. And I'd like to echo that. I think this was an absolutely wonderful talk, and we really appreciate you coming to share your work with us. And while I have everyone on the line, I'll mention that our next webinar is November 16th at 2 p.m. and it will focus on data science and in the agriculture industry. And I think it'll be a really good talk, not only showing some of the methods and skills used in that industry, but also the speaker has recently transitioned into academia. So he's going to be talking about kind of different careers. So I think it'll be a really nice overview and a nice follow-up to this one and some of the work that Nesime has been doing.
Well, thank you for inviting me again. This was great. And I'd like to echo once again that please feel free to reach out to me if anything here sounds interesting, and you know, if you would like to discuss any of these in more detail. Also, the resources that we made available, we did that for the community. So if you try and have any feedback for us on any of these things, please do not hesitate to reach out. We would be very interesting to hear what you think.
Great. All right, well, I guess let's finish a couple minutes early, and thank you again for joining us today.
Thank you.
All right, bye everyone.
Bye.